Hello dear students. So today we are going to discuss about viscosity. Most of the fluids are not ideal ones and offer some resistance to motion. Ideal fluids are basically having some properties like first you can say incompressible, the second you can say it should flow like steady, and third you can say low viscosity. We can sometimes use the word non-viscous. So if any fluid is having these three property, you can say they resemble ideal fluid. This resistance to the fluid motion is like an internal friction analogous to the friction when a solid moves on the surface, and this is known as viscosity. So this is the basically definition of viscosity. This is very much similar like what we have studied about friction in solids. The same role is played by viscosity in liquids. This force exists when there is relative motion between the layers of the liquid. Now let us consider, suppose we consider a fluid like oil enclosed between two glass plates as shown in the figure 10.14a. The bottom plate is fixed while the top plate is moved with a constant velocity v related to the fixed plate. If the oil is replaced by honey, a greater force is required to move the plate with the same velocity. Hence we can say honey is more viscous than oil. You can simply do an experiment. Just take few ml of oil and spread it on the, you can say, floor. First you just spread the oil on the floor. Second time you spread honey on the floor. Third time you can say you spread water on the floor. Now observe yourself. Water moves with greatest speed and honey moves with lowest speed out of these three. So I can conclude water is having less viscosity as compared to these two, oil and honey, and oil is having more viscosity as compared to oil and water, and oil is having intermediate viscosity. Next, the fluid in contact with the surface has same velocity as the that of the surfaces. Hence, the layer of the liquid in contact with the top surface moves with a velocity v, and the layer of the fluid in contact with the fixed surface is stationary. If this is stationary, you can say the velocity is zero. The velocities of the layers increase uniformly from bottom zero velocity to the top layer v. For any layer of the fluid, its upper layer pulls it forward while the layer pulls it backward. For example, if I am considering these three layers, one, two, three. So if I use some names for these layers 1, 2, 3. Now, what if you focus about layer 2? Layer 2 is pulled forward by layer 3 while it is pulled backward by layer 1. So, this is explained here. This results in the force between the layers, and this type of flow is known as laminar flow. So we can have different type of flow: laminar flow, streamline flow. The layers of liquid slide over one another as the pages of the book do when it is placed flat on the table and the horizontal force is applied to the top cover. When a fluid is flowing in a pipe or a tube, then velocity of the liquid layer along the table axis of tube is maximum and decreases gradually as we move toward the walls where it becomes 0. Let us go to the figure 10.14b. The velocity on a cylindrical surface in a tube is constant. So let us explain this by looking into the picture. Like this was the bottommost layer AD, and this was the initial topmost layer BC. Now it is very much similar, like if the pipe diameter is length L, this one from here to here. Okay, so this is a pipe cross section given. Now what they are saying, look यहाँ पे वेलोसिटी 0 है, थोड़ी सी इंक्रीज हुई, थोड़ी सी और इंक्रीज, इंक्रीज 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 इंक्रीज, एंड मैक्सिमम इज ऑन द टॉप मोस्ट लेयर वी. दैट इज वाई देखिए यहाँ पे थोड़ा सा टेंगुलर सेक्शन आ जाता है. इट्स कीप इंक्रीजिंग एंड दिस वन. ओके, एंड यहाँ से यहाँ तक डिस्टेंस ट्रेवल किया है, डिस्टेंस इज डेल्टा एक्स एंड दिस इज स्पीड इनटू टाइम. ये बहुत इंपॉर्टेंट पिक्चर है. अगर ये आपके पाइप का क्रॉस सेक्शन दिखाया हुआ है, ये पाइप के आउटर एजेस है, यहाँ पे पानी का फ्लो है. अब देखिए जो सेंटर लाइन है वहां पे वेलोसिटी मैक्सिमम है. सॉरी, उससे ऊपर नीचे वेलोसिटी घटती जाएगी ड्यू टू विस्कोसिटी. तो आप देख सकते हैं यहाँ वाली वेलोसिटी का एरो लेंथ मैक्सिमम है, देन इट ग्रेजुअली डिक्रीज. और आपने देखा भी होगा पानी का फ्लो अगर रिवर में देखा है तो मैक्सिमम होता है सेंटर में, और यहाँ पे क्योंकि वो इस सरफेस के साथ टच कर रही होती है, वाटर का फ्लो रिवर में अगर देखा है तो यहाँ पे इस सरफेस को टच कर रहा है तो ज्यादा फ्रिक्शन आता है यहाँ पे सॉलिड और लिक्विड में, तो यहाँ पे स्लोएस्ट होता है. A larger a layer of liquid sandwiched between the two parallel glass plates in which the lower plate is fixed and upper one is moving to the right with velocity v. Velocity distribution for viscous flow in a pipe. This is represented in the picture. Now, on the count of this motion, a portion of the liquid which is at some instant has the shape ABCD. Take the shape AEFD after a short interval of time, delta t. During this time interval, the liquid has undergone a shear strain of delta x by L. because you can find from the last chapter there was tan theta and that was delta x over L. Since the strain in a flowing fluid increases with time continuously, unlike a solid, here the stress is found experimentally to depend on the rate of change of strain or strain rate, you can say. So delta x by L into delta T, and delta x by delta T is V over L instead of strain itself. The coefficient of viscosity, pronounced eta, for a fluid is defined as the ratio of shearing stress to the strain rate. Here we have to use rate. This is the definition for coefficient of viscosity. It is asked in question paper frequently. Eta is shearing stress, stress is force by area, and strain rate, velocity over L. So F into L, V into A. The SI unit of viscosity is Poisson, Poiseiiule, represented by PL. Its units are Newton second per meter square, or you can say Pascal second. You can easily find the dimensions, and the dimensions will come out to be m1 L minus 1 T minus 1. Let me explain how they came. Generally, thin liquids like water, alcohol, they are less viscous, and thick liquids like coal tar, blood, glycerin. There are coefficient of viscosity values for some common fluids. We point out two facts about blood and water that you may find interesting. As tables indicate, blood is thicker, more viscous than water. Further, relative viscosity, eta over eta of water of blood remains constant between 0 degree and 37 degree Celsius. So these are the inferences you can make from the table. This line is very much important. The viscosity of liquids decrease with temperature while it increases in the case of gases. So you have to look about the state of matter. If it is liquid, viscosity is 1 over temperature, but if it is for gas, it is proportional to temperature. Gas, and this is for liquid. Okay, now we will discuss about the how the dimensions came out like m1 L minus 1 T minus 1. This is all about the viscosity part. Okay, this is very much easy to calculate dimensions. This is present in the first book, units and dimensions. Now just recall the formula for coefficient of viscosity. Force is mass into acceleration. So dimensions are m1, acceleration is L1 T minus 2. This is length, so you can say L1. This is velocity, m0 L1 T minus 1. This is area, L2. So L1 will become L2, and you can say m1 L minus 1 T minus 2 plus 1, because this minus 1 will go upside. So you will get m1 L minus 1 T minus 1. These are the dimensions for coefficient of viscosity. The thing is Stokes law. This is also an important law. When a body falls through a fluid, it drags the layers of the fluid in contact with it. Like if you drop a spherical marble, I can say, in water. And if there is water, you can see when this is going downward, the adjacent layer will go downward with it. A relative motion relative motion between the different layers of the fluid is set, and as a result the body experiences a retarding force. Now why this is force is retarding? Because you will be getting acceleration as negative. Because when you just put a spherical ball or something in water, it will go downward, but the fluid will try to decrease its speed. Falling of a raindrop and swinging of pendulum bob are some common examples of such motion. Now, what is happening in the case of raindrop? The raindrop speed keeps on increasing as it comes down, but the value of drag force is also increasing on it. It is seen that viscous force is proportional to the velocity of the object and is opposite to the direction of the motion, and the other quantities on which the force of depend are viscosity of the fluid and the radius of the sphere. So we are considering a spherical raindrop. So the viscous force depends on velocity of the object as well as the radius of the sphere. And this is mathematically given by a scientist, Sir George G. Stokes, an English physicist scientist, enunciated clearly the viscous drag force Fs. This force F is 6 pi eta AV. A, you can say, sometime you can replace it by radius. F is 6 pi eta RV. This is known as Stokes law, and we shall not drive Stokes law. So derivation is not in your syllabus. So this expression is basically Stokes law. You can use R in place of A for interpreting with radius. Next, this is an interesting example of retarding force which is proportional to the velocity. You can see this force, if I look at this equation, F is proportional to velocity. To the power 1. We can see, we can study its consequences on an object falling through a viscous medium. We consider a raindrop in air. It accelerates initially due to gravity. It will go like speed up, speed up, speed up due to gravity. But as the velocity increase, the retarding force also increase because they are linearly dependent. Finally, when viscous force plus beyond force becomes equal to the force due to gravity, the net force becomes zero, and so does the acceleration. The sphere raindrop then descends with a constant velocity, and thus in equilibrium, this terminal velocity Vt is given by this equation. So why we are saying using a word terminal velocity? Like initially the raindrop was here due to gravity, its speed will increase, but there will be one time like this is the gravity impact downward, but force of buoyancy and viscous force they will balance force of gravity. So that force will be zero, acceleration will be zero. So it will be moving with the constant velocity, and that constant velocity will be termed as terminal velocity. And then it is given by 6 pi eta r vt. Vt stands for terminal velocity is equal to 4 by 3 pi r cube rho minus sigma into g, where rho and sigma are the mass densities of sphere and fluid respectively. So on simplifying, you will get it as like terminal velocity is 2 a square. You can say r square also if you are replacing a by radius r. Rho minus sigma g over 9 eta. So the terminal velocity depend on the square of the radius of the sphere, and it is inversely proportional to the viscosity of the medium. From this equation you can relate. Okay, this is all about the two topics for today. Thank you so much. Next we will do in next class.